we've looked at a couple of things and I want to put them together. We've said that a current carrying wire, when in the presence of an external field, feels a magnetic force. We've also said that a current carrying wire creates a magnetic field. So this is going to be a video about the force between parallel wires. If I've got a wire here that carries a current maybe to the right, and I've got another wire here that carries a current, and let's go again to the right. These two wires are going to exert a force on each other. I'm going to label these wire 1 and wire 2, and I want to look at just one of these for a little while, and I'll do the second half of it pretty quickly, honestly. So wire 2. Wire 2 is sitting here, and it is carrying a current to the right. Sure, we know that wire 2 will experience a force, I2 times length 2 times the B experienced by 2, so I'm going to say B at location 2. Wire 2 also produces a magnetic field around itself, but it doesn't produce a magnetic field on itself, right? It'll produce magnetic fields around itself this way, but at the center it doesn't produce a magnetic field on itself. So this B at location 2, this is a magnetic field not produced by wire 2. Right? It has to be an external magnetic field. But wire 1 is over here, and wire 1 is producing magnetic fields around itself. So it's over here producing magnetic fields this way. Now what do we know? If we were looking at wire 1 from the side like this, we would see the current coming at us, and we would see these magnetic fields creating circles around it. Which means at this location below wire 1, but in the plane of wire 1, I get a magnetic field that points into the screen. Up above, I get a field that points out of the screen. Everywhere below wire 1, I get a magnetic field that points into the screen. As I get farther from wire 1, that field gets weaker, but it continues to be there. Everywhere above, I have the same story. I have fields that come out of the screen, but the farther I get from wire 1, the weaker those fields become. This wire 1, this field that it produces, that actually is external to wire 2. So when I get down here to wire 2, to that location, I'm going to get a field produced by wire 1. Now I need some pieces. If these wires are a distance of d apart, then the magnetic field due to wire 1 at the location of wire 2 is going to be mu naught I1 over 2 pi times the distance from wire 1, which is d. If I put those together, I now get a force on wire 2 that looks like I've got a mu naught, an I1, an I2, maybe I can color code these. I've got a mu naught I1 over 2 pi d, and all of that comes from B1. I also have this I2, and I also have this L2. Now there's a little bit of a problem, and it's this. This wire is infinitely long. That's the assumption we're making when we're using this formula. If this wire is infinitely long, I am taking my force, taking a bunch of stuff, and multiplying it by infinity. That's not going to work so well. So what I do instead is I want to look at the force per unit length. Now the force per unit length, that's just F2 over L2. So all I'm doing is dividing out this L2. And now I'm going to stop with the color coding for a moment. And I'm going to have a mu naught I1 I2 over 2 pi d. I should also be able to figure out the direction of this force. So that's the next step. Wire 2 is carrying a current to the right. I said this was wire 2, so let's call that current 2 and current 1, right? Wire 2 is carrying a current to the right. It feels an external magnetic field that points into the screen. So right hand rule, I'm putting my open hand, I'm putting my thumb to the right, my fingers point into the screen, and I get a force that points upward this way. There is the force on wire 2. So my force on wire 2 per unit length is going to be mu naught I1 I2 over 2 pi d, and it's going to point upward. I can do a little bit more. This is only one of the two wires that's present. I also want to be able to look at the force on wire 1. Now that was a lot of work to get this, right? None of it was particularly hard work, but it was kind of a lot. So let me think about this. Force 2, this is the force on 2 by 1. The force on 2 by 1. I'm going to also look for the force on wire 1 I'm looking for the force on wire 1 by wire 2. Newton's third law says that these two, the force that A exerts on B is equal to and opposite the force that B exerts on A. It guarantees that these are equal in magnitude and opposite in direction. So I don't have to do a whole lot of work, honestly. I can look at this and say, there's my force on wire 2. It points upward. So my force on wire 1 per unit length is going to have the same exact magnitude. And it's going to point downward, which means these two wires, these two parallel wires carrying current in the same direction as each other, are going to attract each other. That might be a little bit more clear if I throw wire 1 up above wire 2. These two are going to attract each other. If they were carrying currents in opposite directions, and you can work through that part just to make sure that you are convinced, if they were carrying current in opposite directions, they would repel each other. That's it. That's the force between two parallel wires that carry current. They have aspects of both, right? D is the distance between them, there's D, and then they have both currents right in the formula. So everything's accounted for. It's just a matter of the direction on each, and those have to be equal and opposite.